Hello everyone, myself Professor Tushar Gujrati from SND College of Engineering, Yeola. Today we'll study experiment number 10 from the subject mechatronics, and the name of experiment is study of modeling and analysis of a typical mechatronic system. So here we are going to study modeling and analysis of typical mechanical system. Okay. So what is the objective of experiment? To model a typical mechanical system and perform its time domain analysis. Okay, this is the objective of the experiment. So mechanical system, it is made up of spring mass damper type system, and we have to perform its time domain analysis. Okay. So what is outcome of this experiment? Model a translational mechanical system using the transfer function approach. So students must be able to understand how we can use transfer function approach for modeling translational mechanical system. Second outcome, student must be able to estimate poles, zeros, natural frequency, damping of the system. And third point, student must be able to perform the time domain analysis of this system so as to determine percentage overshoot, rise time and settling time. So these are time domain analysis parameters that student must understand. Okay. So this is the mechanical system is shown. So it consists of one massless cart. So on that cart, what is placed? One mass is placed having rollers. So this is one massless cart is shown. Okay, it has rollers, and one mass is shown. Okay, that is also have rollers, and it is connected with spring and damper. So here K indicates spring and B indicates damper. Okay. So in this diagram, displacement of cart is U. Okay, this is displacement of cart U, and here it is displacement of this mass is Y. Okay, this you understand. Now for translational systems, Newton's second law states that summation of F is equal to m into A, that is force is equal to mass into acceleration. So A is nothing but m into y double dot. Okay, so this is here Newton's law. So now here in the Newton's law, m is mass, A is acceleration of the mass, and summation of A is the sum of forces acting on the mass in the direction of acceleration. Okay. So now this Newton's law we have to apply here. So here summation of forces that we have to take. So here let's discuss on diagram. So here two types of displacements are shown. One is y and one is u. Okay, y is of mass m and u is of massless carts. So what happens? So this spring, because of this spring, force is applied. So in this case, displacement of mass m is y and displacement of cart is u. So overall displacement is y minus u. Okay. So you assume that this mass has displacement of y minus u if you consider both the displacement. So because the spring force which acts, it is in the form of k into y minus u. This is the spring force. Okay. Spring force is nothing but force is equal to k into x. This is the formula for spring force. Okay. That's why we get k into y minus u. And similarly for damper. Damper, what is the formula of force for damper? It is B into x dot. Okay, B into displacement dot. So here B into y dot minus u dot. Okay, so like this force. So there are two forces acts on the mass m. One is spring force and one is damping force. So k into y minus u and B into y dot minus u dot. So same thing here it is written. So B into y dot minus u dot. This is one damping force and this is spring force. So both acts in one direction is equal to the acceleration of the mass into acceleration of the mass. Okay. So rearranging the terms. If you rearrange the terms, we get m into y double dot plus b into y dot plus ky is equal to b into u dot plus k into u. So like this we'll get terms if you rearrange the terms. So now again I have written same equation here, m into y double dot plus b into y dot plus ky is equal to b into u dot plus ku. Now apply all the initial conditions 0 and take Laplace transform of above equations. Now we are taking Laplace transform of above equation. So what is Laplace transform of m into y double dot? So m into y double dot means m into s square y of s. If there is double dot is shown, means double derivative, then we have to multiply by s square, m into s square y of s. Okay. Now in the second term, b into y dot, only one derivative is there, that's why it is multiplied by only s, that is b into s y of s. Okay. Now third term, ky. So here there is no derivative, that's why we can write directly as it is k into y of s. Similarly next, b into u dot. So here is one derivative, that's why b into s into u of s, multiply by s. And last term as it is ku means k into u of s. Now here collect similar terms. So y of s you take common. So in the bracket will remain ms square plus bs plus k. And here you take u of s common. So in the bracket it will remain bs plus k. And take the ratio y of s upon u of s. So the transfer function is this, bs plus k divided by ms square plus bs plus k. So this is the required transfer function of the system. So now, assuming the values of mass, damping and stiffness to be m equal to 1, k equal to 2 and d equal to 0.5. So let us assume the values m, k and d and put in the formula. So equation will change something like this, 0.5 s plus 2 divided by s square plus 0.5 s plus 2. This is the transfer function required. Okay. Now estimation of poles and zeros. Now we have to estimate poles and zeros from this transfer function. So the location of poles and zeros of the spring mass damper system is determined from transfer function which was derived in the previous section. So now we can derive poles and zeros. So what is poles? The poles of a transfer function are the roots of the characteristics equation in the denominator of the transfer function. So if you find roots of the denominator equation, it is called as poles. Okay. Roots of the denominator equation are called poles and they are determined as below. So here the denominator equation is s square plus 0.5 s plus 2 equal to 0. This is denominator equation. Okay. So now we have to find out roots. The formula you know for finding root. So what is the formula? Minus b plus or minus under root of b square minus 4ac divided by twice a. b square minus plus or minus 4ac divided by twice a. Now here these are a, b and c coefficients. So you have to put in this formula. So we get the roots. So you do addition and subtraction, you will get roots as minus 0.25 plus or minus 1.39 I. So these are the poles. So now you read the paragraph. The poles determined above are a complex conjugate pair. So they are complex conjugate pair, means one is plus and one is minus. In this pair, the real part is negative. So real part is negative. Thus we can conclude that the spring mass damper system is relatively stable. So this system is relatively stable. In addition, the poles being a complex conjugate pair helps concluding that this system is underdamped system. So this system is underdamped system. So here I have written underdamped system and it is relatively stable system because the poles are plotted in the graph. Okay. So the location of poles will be here on the negative side. Okay. One will be here and one will be here. So this left hand side portion, left hand part, okay, this part is stable part and right hand part is unstable part. So if your poles are in left hand side, okay, then they are called as relatively stable system, and damper and this system is underdamped system also. This you remember. Now zeros of a transfer function are nothing but roots of the numerator equation. So roots of numerator equation are 0.5 s plus 2 is equal to 0. Therefore root is minus 4. So this is the zero of our transfer function. Now estimation of natural frequency and damping. So one way to determine the natural frequency of a system is by solving below equation, that is omega n is equal to under root of k by m. This is the formula. Now using this equation, the natural frequency omega n of the spring mass damper system is omega n is equal to under root of k by m. So k and m are known to us. 2 and 1. Therefore answer is 1.414. This is the natural frequency. Now another way of determining the damping factor zeta and the natural frequency omega n is to compare the pole location with the generic equation for the location of the pole. So this is generic equation is given now. Minus zeta omega n plus or minus I omega n under root of 1 minus zeta square. This is the generic equation. Now since the natural frequency is determined to be 1.414, okay, the damping factor zeta can be determined by comparing the real part of the poles previously determined with the generic real part. So previously we have determined our equation. What is our equation? Previous equation. So previous equation is nothing but minus 0.25 plus or minus 1.39 I. Okay. So it is minus 0.25 plus or minus 1.39 I, something like this. So you compare this now, these terms. So we get 0.25 is equal to zeta into omega n. Therefore omega n is equal to 1.144. That's why zeta is equal to 0.177. So damping factor here is 0.177 and frequency is 1.414. Okay, this is our answer by comparing to the generic equation. So now time domain analysis of spring mass damper system. We have to perform time domain analysis also. So there are 4 to 5 definitions are important. So first is percentage overshoot. So definition is it is the amount that the response overshoots the steady state or final value at the peak time, expressed as percentage of the steady state value. So when output produces the maximum overshoot or the maximum peak is observed, that is called as percentage overshoot from the steady state value. So if this is steady state value, in this maximum peak is called as overshoot, percentage overshoot. Okay. Now rise time. The time required for the step response to rise from 10% to 90% of its final value. Okay. It is called as rise time, to increase from 10% to 90%. What is delay time? Time required for the step response to reach up to 50% of final value. Means for reaching 50% of final value, time required is called as delay time. Settling time is time required for the step response to decrease and stay within a specified percentage of its final value. Means time required for settling the output, the time when output gets settled down, plus or minus 2 or 5 or 10% error, that is called as settling time. And last one, steady state error. It is the difference between the output and the reference input after the steady state has been reached. So after the output is settled properly, at the time the difference between input and output is called as steady state error. So that may be plus or minus 2% or 5%. Okay. Now this is the formulas shown here. So as we have already calculated, omega n is 1.414 and zeta is 0.177. So this we have to put in the formulas. So first formula is maximum percentage overshoot, 100 into e raised to minus pi zeta divided by under root of 1 minus zeta square. So here you put values and you will get this answer, that is 58.16%, maximum percent overshoot. Now second is settling time, 2% settling time. The formula is Ts is equal to 4 upon zeta omega n. So only put the values, we will get answer as 15.98 seconds. And last one is rise time. It is Tr is equal to 0.8 plus 2.5 zeta upon omega n. So last answer is 0.88 second. So like this we can do time domain analysis of the given system. So after studying this experiment, the conclusions are something like this. So the transfer function model of the system is given by like this. So this we have calculated in the first step. Y of s upon u of s is equal to 0.5s plus 2 divided by s square plus 0.5s plus 2. This is our transfer function. From this transfer function we got the poles. So poles are minus 0.25 plus or minus 1.39 I. How we calculated poles? The poles are nothing but roots of the denominator equation, roots of this equation. Okay, that is called as poles. Now from pole we can conclude that since the poles are complex conjugate pair with negative real part, it can be inferred that the system is stable under damped system. So it is here system is stable and under damped system because of poles are negative. Now we have also calculated zeros of the system located at minus 4. So from this numerator term, if numerator term is equal to 0, then we get the 0 are located at minus 4. We calculated natural frequency and damping factor also. So natural frequency is 1.414 rad per second and zeta is 0.177. And by using this omega and zeta, we calculated maximum percentage overshoot, settling time and rise time. So like this we have performed this experiment. So thank you so much all of you for watching this video. Thank you.